Thank you for the very generous introduction. Hello, Halhe. Did I pronounce it correctly? Yeah.
You were fine.
Hi,
Yeah.
nice to meet you. Yeah. Oh, cool. So I'm provide before I share my screen, I would just like to frame a little bit of what I want to discuss with you guys today. So obviously, I'm here to talk about information. So we live in the so-called information age, which is a term that we use quite casually every day. But actually, I argue that this casual use of the term benighs the profound complexity behind it. And we often take it for granted that information is just what it is, which is a straightforward commodity that we store, moves, and consumed. But as philosophers and scientists like Robert Logan have argued, that information is actually not a simple, straightforward idea. Rather, it is quite a slippery concept used in many different ways, in many different contexts. And for the most part, we don't really have a clear understanding of what exactly information is. So today, I intend to show you how information is a relative and relational occurrence, and it's more a process than a static object. And it is only through a multidisciplinary understanding of information that we can begin to grasp its vibrancy and the potential for architecture. So today's journey will explore how the principle of compression, which is the act of making information efficient, can be instrumentalized to create systems that can actively resist disorder and anticipate the future of urban development. And this is the core of the thesis that I wanted to share, which is called entropic architecture. Just a little problem, I couldn't share my screen.
Maybe you need to give permission, somebody from there.
Yeah, you have the permission now. She just.
Cool. Yep, got it. Okay. Yeah, so I've got entropic architecture here with the neg in brackets. Yeah, cool. So the presentation is an assemblage of ideas that try to map the vast and complex territory that sit at the intersection of digital theory and urban design. And I've framed it around 5 parts. First, we understand what is information and dive into the fundamental dichotomy. Is information entropic or negentropic? And second, we will unpack how compression works and why it is essential engine for information processing. Then we will try to define what is negentropic architecture and introduce key concepts within this discourse. And of course, we have to dive into practice. So I will show an example of how these ideas can manifest at the urban building and social economic scale through a small AI-driven experiment. And finally, I will propose a framework for the future, which is how to synthesize this concept into a scalable method. Ultimately, this is about decision-making processes in design and how we can actually diversify choices in the system, enabled by information prediction and participation. So we will trace through a series of events at the beginning of the information age to reflect on how and what we can do as designer in today's increasing generative design culture. So let's get started. The slippery concept of information. So the word information actually emerged as early as 1300s and is derived from Latin via French, and it combines informare, which is to give form to the mind, with the suffix ation, which denote a noun of action. Information, therefore, is fundamentally a process, which is the action of molding the mind. And this immediately raises some questions for me. So is information a universal invariant concept? Is it merely pattern extracted from randomness, or is it a representation of energy? Well, actually, the modern quantitative conception of information is the child of the 20th century, and is actually born from the urgency of World War II at the dawn of the digital era. The year 1948 saw the birth of these two publications that changed the way we think of information. The one to the right dealt with the nature of information and the relationship to the tools to operate information. The one to the left dealt with how information can become the tool itself. While both consider how information becomes a point of value during creation, the right one saw value as compression and bandwidth. So how much we can express within a transaction as opposed to semantics or scarcity in the market. The left one saw value as the ability to preempt within a statistical structure. And so Claude Shannon is the father of information theory, and his work lived in a time when a democratization of telephone communication was at the forefront. Oh, sorry to interrupt. Is it okay to pause the mic in the classroom?
Yeah.
Thanks. Yeah, so this is the landmark publication where Shannon expressed the potential he saw in encoding messages with zeros and ones to help prevent them from being corrupted by noise when transmitted across distance. So this is actually a major breakthrough from the conventional analog-only view of signals that is enabled by waves and modulations at the time. So in very simple terms, Shannon defined information as the quantification of surprises. So consider this presentation as a signal being transmitted to you by a Zoom. If you already understand information theory, then likely this presentation contains little information because there are no surprises. So surprises are entropy, which is why Shannon equates information with entropy as a mathematical formula of communication. So entropy was defined to be the lack of order or predictability. Shannon's information entropy is the measure of the amount of information contained in a message as opposed to the portion that is determined or predictable. So if a message is perfectly unsurprising, there's no information to the receiver, and the amount of information is relative to the receiver and the machine generating the message. And so it must be bounded in the design of the system, which is why Shannon basically have his paper written in 3 parts. The first part talks about compression, which is the minimum number of bits someone need to retrieve a piece of information. Second is communication, which is the channel capacity, what we call bandwidth today. And it calculates the physical constraint. So like noise and heat generated from electrons circulating. And bandwidth basically represent the physical infrastructure as a mathematical model, what we know as partial differential equations. And the third part, he actually calculate the probabilistic structure of natural languages. So he dealt with human communication by looking at the relationship between binary encoding for English and the structural redundancy of the language, so entropy, and the irrelevance of semantics to the quantitative measure. So together, these 3 parts define the limits to communication. And today we will focus only on the first part, which is compression. Well, why do we look at compression? Because it's actually closely tied to the limits of intelligence. For instance, many AI models are essentially compressing language. GPT, which is generative pre-trained transformer, are essentially massive compression systems. They compress fast data sets, including text, images, sounds, into mathematical weights, which is a set of parameters that capture the patterns and meanings in a data set rather than the exact data reproductions. So it is a form of lossless compression where some details are discarded while preserving essential concepts to generate new outputs. And very relevant to architects in a generative design field, autoencoders are compression par excellence, which form the basics to many 3D generative algorithms that encode dimensional data into a latent space, so the blue squares you see in the middle, which is then decoded to extract essential features or generate variations of the reconstruction. So compress, decompress. And essentially, it's not so different to architects' design intelligence. So I can give an example. For instance, if an architect has 10 years of experience, he will be able to see a space and kind of know immediately what's suitable for that space as a design. And the architect is actually working based on all the precedents that he or she have seen in life, but they may not be able to point fingers directly at where they saw the precedent before. So the architect's intellect is the latent space of kind of like the AI that compresses the knowledge and then decode it depending on the context or problem raised. So what I did just now was to parallel and reflect on what intelligence is. And this process is called reverse engineering, and it's quite useful because it not only helps us to understand how information work in an intelligent process, it actually enables us to understand not just AI as a tool that we can better use, but our own intelligence in general so that we can recursively self-improve. And I'll use this method throughout the whole presentation. Now, if we go back to how we compress information, ask the question, first we must know what defines a unit of information. And we call a unit of information as a bit, which is short for binary digits. Very smart. It's actually used by Shannon's colleagues at the Bell Lab as early as the 1940s. But that is a popular notion of a bit, which is a storage bit. At max, it's a 1 or 0. So a storage bit contains at most 1 bit of information. But Shannon's bit is a unit of surprise. So he defined a quantitative measure of information relative to the probabilistic distribution of English and used that to encode the message. So information is not just what we say, but the unpredictability in what we say, which is the information entropy. So as entropy increases, we can encode more information per character, and our ability to compress increases. And so compression is actually a concept that exploits redundancy, the lack of surprise, to reduce a representational size of some message or an idea. So there's a fun story that Shannon didn't actually know what to call his measure at the time. And John von Neumann, which is another very famous mathematician, he advised Shannon to use entropy because nobody actually know what entropy means. And that will give Shannon an advantage in any debate. So this basically showed two things. First, John von Neumann is a very charming interdisciplinary polymath that appears in almost every story in the 20th century science. And so I really advise to actually look at how he think about things, especially intelligence. And second, no one can really be sure what entropy is, even the brightest minds on Earth. So don't worry if you feel like things are a little fuzzy for you. I might actually be wrong about the whole thing myself. So in fact, another famous mathematician of the time, Norbert Wiener, had a different understanding of information and entropy. So he wrote very beautifully that this amount of information is a quantity which differs from entropy merely by its algebraic sign and a possible numerical factor. So put simply, that Shannon equates information with positive entropy, but Wiener actually equates information with negative entropy. So how can they both be right? And it's actually because Wiener held that information is negentropic, as the environment contains no information, and information is constructed by living beings through prediction. So Wiener said that the more probable an event, the less information it gives. And so predicting less likely event will give more information. But for Shannon, who models information content by improbability in messages, he thinks that increasing entropy increases information. And so Wiener's emphasis is to make the world more predictable by reducing surprises to create more usable information. And even though they don't perfectly agree on what the information is, they actually share a common ground. So if you actually, it's very interesting to read Claude Shannon's paper. You can skip all of the equations. But if you look in the footnotes, that he would credit communication theory to Wiener for much of its basic philosophies, including time series, linear prediction, data filtering. So if anyone's interested to look at where ideas come from, I strongly advocate for you guys to read these texts from these famous mathematicians. And so why do they have different views on compression and information? It's actually because all of these scientists work in the World War II, especially Shannon and Weiner, they work at anti-aircraft fire control. So it's a problem of how to shoot your enemy's aircraft down. And Shannon was obviously more dedicated to the communication and encryption of information, where the fewer bits you need to use to retrieve a piece of information, the better it is for wartime communication. So that's Shannon's entropy. Whereas Weiner was working with how you can compress the time operation between the shooter, the machine, and the aircraft. So the more information you derive from a system, for instance, the aircraft flying trajectory, the less surprises you get, the more likely you hit your target. And so less entropy is better, and thus negentropic. So Weiner actually realized that the problem of concern was compressing the limits of engineering knowledge at the time, and it falls between the tools of established fields of expertise. And anti-aircraft control is actually an interdisciplinary problem that encompass fields of dynamic system, corrupted data, information feedback, and the most unpredictable parameter, which is human operators. And so Weiner would be the person that you find that after the war goes on to establish the field of cybernetics, which is one of the first interdisciplinary scientific fields at the time. And cybernetics also has a long history with architecture, but we're not going to cover that in this talk. But I highly recommend to actually dive into that. And so Weiner began to think from an engineering perspective how to simulate a gun-pointed situation in order to preempt the opponent's decision, which is one of the first incidents you see in history about human-computer interaction through information transmission. So what Weiner did practically was to take some signals he received in time, so these waves and modulations, which are quite complex to process, and we often study in frequency, and he actually moved it to the time domain. So from the time domain to the frequency domain, which makes it easier to filter out the insignificance with the point calculation, as you can see, which compresses redundancy in time and compresses the time needed for the prediction. So that's what mathematician calls the Fourier transform, and it basically boosts the way we can predict in a context via feedback and the capacity to act before certain risks are realized. And so prediction is actually a negentropic action. And this is what the cybernetic loop is all about. So by pressing the engineering limits and setting a field between these established disciplines, Weiner approached this problem as an engineer through information transmission. If we think about the same problem from another angle, there is a quote in the paper which asks, can we find a measure of how much choice is involved in the selection of the event or how uncertain we are of the outcome? And so in a way, if we go back to Shannon, information is measured relative to the amount of choice within a stochastic process. And he refers specifically to the Markov process, which is a random process in which the future is independent of the past given the present. And this time relationship is summarized by the notion of a state that evolves over time according to the probability distribution. And so if we know the state of a system at any point in time, not only provide a good description of the system at that time, it does so to capture the critical information we need in order to answer questions about the future evolution of the system. And so prediction for Weiner can also be positive entropy. And at this point, we ask ourselves, so why do we care so much about whether information is entropic or negentropic as architects? Well, because it actually formed the basis to how we think about probability problems. And probability will inform future ways in which architects respond to urban issues. So I'll give this example of the Markov blanket, which actually facilitate the transmission of information inside and outside a system, and it defines the boundary of a system statistically. And it's through a set of states with conditional independence. So if one changes, then 2, 3, 5, 4, 6, 7 will also change. And those who have coding experience will see the implication that the Markov blanket is actually a way to describe entropic tendency of an autonomous system. And so compression here doesn't mean that we have fewer choices, but it is that we should clarify the choices in the system. And at the horizon of the blanket where an individual, so where the system meets its environment. And from this example, we begin to see the implication for design. So as an act of design itself is both entropic and negentropic because it should create surprises and order simultaneously within a system. And thus, as designer, we must seek to create systems that minimize entropy locally to help us make decisions, but actually maximize entropy globally, so it creates more choices. Meaning that we can create local order through observable patterns, but we should always diversify surprises in the overall system. And this order is not the Cartesian grid that modernists have built cities on, but a statistical boundary of a system. And this brings us to the second part, which is how we can translate these ideas into its architectural significance. And so through this lecture, I hope to bring the message that for architects, compression and information is not simply a digital tool, but it's a fundamental design principle. So in this light, the entire design process can be seen as a chain of oscillating compression prediction protocols, so minimize and maximize entropy. From the nebulous problem to the concept, a concept is a highly compressed idea to develop design, which is a detailed prediction, to the construction of schematic documents, which is a compressed set of instruction, and to building drawings, which is a set of instruction to realize the actual building. So at each stage, the goal is to create a more efficient, less redundant, and more predictive representation. And so today, as architects, we must work with digital tools that help us to collect, generate, and analyze, manipulate information, especially with AI, which actually accelerate this process. So it means that recognizing information has value at the point of creation, shaped by constraint. And compression isn't just making files smaller, but it's actually a design of choices. And with this understanding of information, we can now define our central theme. That negentropic architecture is a design philosophy that actively negotiates surprises and order within a built environment by defining the statistical boundary of a system. And this concept moved from an abstract theory to tangible impact across multiple scales. If I take the notion of a BIM model, for example, essentially a compressed representation of a building that eliminates the redundancy of a full-scale construction to allow for analysis, prediction, and preemption of design conflicts, energy performance, and spatial experience. Now, governments worldwide are increasingly advocating for using BIM and digital twin in architecture and construction projects. But from our theoretical standpoint, this advocate only half of the equation, which is to fulfill net entropy. However, it actually needs a counterpart to diversify choices in the system, which is to increase entropy. And if we do not have guidelines in architecture to help balance this chain, we will easily fall into a self-assimilating environment that will be increasingly ordered, increasingly homogeneous, increasingly negentropic, but also repeating the downfall of modernism planning. And this problem statement basically shaped the example that I will show in part 3. From theory to practice, I will show the case of 21E8, which is a project that I work with a blockchain startup in New Zealand to try and test how we can decentralize indexing in a common data environment for BIM in order to advocate for collective actions in urban design. And so we will look at how we can become a peer-to-peer architectural common through integrating BIM, AI, and CDE, where our built environment deserve more inclusive and equitable and participatory methods of design. And at the core of the problem is the lack of means to collectively discover the value in a piece of information, and the ability to collaboratively rank them. So imagine the scenario that you are an architect for a building project. You have collected 1,000 pieces of information or ideas in a common data environment. And you have to search through this data environment for the most valuable piece of information that can inform your decision of how to design, for example, a child-friendly space. The first piece of information that comes up in a search might greatly influence how your decisions are made. And if we imagine this in a scenario of using a generative AI to generate an image as an inspiration for you to design, the problem goes the same. What determined how much weight was given to a certain data point in a system? And this is how the algorithm of ranking and the algorithm of generation dictates subconsciously how architects make decisions in a design process. And it also shows us how information is deeply connected to governance and decision-making. Now, of course, anyone can hire a project assistant to rank the information or label them one by one and train their own AI algorithm, but you still run into the same problem of how we can define the subjective parameters of a design in order to give weight to a piece of information. For instance, if I want to design a community center, what my system perceives as valuable information might not align with what user actually think is valuable, and thus it will affect validity in our design decisions. Along this line, the study investigates two interrelated questions. So how can value be transacted from peer-to-peer amongst a network of architectural content contributors through decentralized indexing? And consequently, how can value be captured and realized within these data transactions and in what form? Essentially, it tries to ask how to define entropic and negentropic operations within an architectural decision-making systems. And this is where we propose a decentralized information ranking method, which is a collective indexing infrastructure that turns any data environment into a peer-to-peer system. So at the core of the innovation is what I call a proof of architectural work. So a decentralized system like blockchains, they normally use a proof of work, which is a mechanism that assists the community to reach consensus by validating how legitimate a transaction is. However, this heavily relies on whether an individual has the computational power to participate in this mechanism. For instance, you will need a GPU to be able to participate. And this would mean that people with higher financial capacity can more easily influence the system, thus creates inequality in a society. And so financial speculation is the tool that the world of investment uses. But when it comes to architecture, I argue that this will become a problem because excessive speculation will cause a lot of damage to architectural projects, which essentially builds a universal basic service for its people, which is sheltering them. And so these kind of calculations should not be driven solely by profit, but more through human-centric parameters. And the difficulty is how do we define these parameters? And so the proof of architectural work is a mechanism that tries to quantify how an individual contributes to the system in some level, not just through capital and computational power, but also through the architectural work that this individual has contributed to the system. And so it enhances not just system value, but also the quality of the design in the system. And it will allow one to contribute through urban data points. So if you contribute OpenStreetMap, LiDAR scan, social analysis, etc., design content or ideas. So you can also contribute a BIM component, a graph or code, or you can contribute compute, which is a unit of storage or processing. So by contributing work to the system, it will enhance your stake to influence the system decision. For instance, you would be able to vote on a piece of information to rank the content and generate decentralized consensus, or you can earn rewards if someone voted for your contribution. And you can earn the reward in data, compute, or token, and not just money. So the goal is to create an ecosystem where you can spend data for data, compute for compute, and not just influenced by capital. And here, a network of competing actors can create harmonious outcome through positive competition. And I'll give an example of how it works. So this is an interface design for the index. So imagine you're a creator. You can upload a sustainable housing design to the data environment. And you will have backer who might think your design is cool, and so they can fold it up by clicking on the link, and it will contribute spare computing power from the backer's computer. And this compute power will be stored as a JSON file, which is a lightweight human readable file locally on their device. So these become a network of computer devices that stores information for the common data environment. And that is a decentralized system. And the backer's vote will influence which design idea come up first in a search engine. So this can help designer who actually spend effort on their design to attract attention, clients, and collaborator while harnessing network effect. So this value flows from peer to peer and is anchored by the blockchain immutably. And these agents, including the creator, the backer, the clients, they will form a community and they will help better design ideas to come up first in a search engine. And this is actually a very basic model of decentralized autonomous organization. However, all of these decentralized network actually faces the same problem, which is that there are always bad people in the world, and bad people can make false proposal to drain the system if we get scammed. And so this is the core problem, which is how do we prevent bad voting? Which means that the community actually does not possess enough knowledge to make valid decisions. And so it will maximize entropy in a system and cause the system to fail. Now, the original person who proposes the DAO idea tried to mitigate this problem through a forking mechanism, which means that if you disagree, you can just open your own chain rather than trying to negotiate with others. But in the context of architecture, this actually leads to a very undesirable outcome, such as priority encumbrance. And so I argued that we need 3 additional agents in the system to mitigate this risk. The first is that we need a validator. A validator earns compute credit by deploying building information modeling to align real-world constraints and test physics-based properties. Thereby, the validator validates proposals. Second, we need an iterator. So an iterator will consolidate all of the recorded history of a design proposal, including users' votes, expert evaluation, and the BIM simulation to generate evolved design options. And so the iterator maximizes entropy in the system to help it to achieve a Nash equilibrium. So by iterating the same option many times, it should converge to a stable design solution where no one has the incentive to deviate from that design. And we also have a diversifier. So it's not enough to eliminate false proposals. It's even more important to make sure that the system has a lot of good design options. So you can increase the chance of successful evolutionary outcomes. And this is what the diversifier does. They will take a validated seed idea, deploy differential variables to them, and generate exponential amount of options from the seeds. And so this is where generative AI becomes handy. And I'll try to demonstrate how this can work through a case study I've done in Hong Kong. So this is the Hong Shui Kiu district. The only thing you need to know that it is going to be a new developed area with transit-oriented development model. And so essentially it used a network-driven approach to planning, and it makes a great design case to utilize a graph as a base diversifier to generate different ways in which urban fabrics can connect with major functional and transit hubs. For instance, this is a very basic network analysis that rationalized the urban fabric through topologies extracted from 4 different graphs: the EH graph, random graph, small world graph, and preferential attachment graph. And each of them have very different properties. For instance, EH graph for regular and they are they're highly algebraic and geometrical. They are very good for stabilizing system into the shortest distance between every point. And so it's good for conceptual design of a symmetrical, balanced urban hub. A random graph is good for modeling unplanned or evolving connectivity. A small red graph is good at optimizing local clustering, and a preferential attachment graph is good to model hub emergence and growth. And if we see these in action, all of these are various models that can be translated as urban network. And we can begin to diversify design option of the urban planning. For instance, if we use a smaller graph, we can use it to optimize clustering of distributed landscape. We can use preferential attachment graph to model local strategic hubs for compact city infrastructure and create minimum ground impact with surrounding ecology. Random graph can be used to model connectivity of self-regulated facades according to a network of sensors and actuators. And network graphs or spatial graph can be used to represent connections between buildings as a series of nodes and determine pathway for floodwater or structural support. So all of these can actually be used as a generator to diversify planning options in a system, given the complexity of the urban fabric. Or we can use it simply as a datum of evaluation according to predefined objectives. Now, of course, all of these are very preliminary and immature proposal that probably a professional planner or programmer can do much better than I do. But essentially, I want to demonstrate how an information system needs entropy calibration at 2 levels. Yeah, so validators and diversifiers are not competitors. They're actually competing agents with collaborative outcomes to help the system achieve a Nash equilibrium. So in plain terms, generative AI should be used to maximize entropy at the interface layer. Beam model manage entropy, which is a directory at the infrastructure layer. And collectively, the system entropy should maximize globally, but minimize locally. And this is intelligence, as essentially this is a system of collective intelligence. And you measure the success of the system through these parameters. On a practical level, influence of bad faulting, where AI's big data patterns and Beam's Newtonian physics ground speculation in reality. But I would also like to clarify some conceptual ambiguities, which are quite important to consider. That first, decentralized indexing is not a traditional database because there are no central database. Instead, an index is a distributed network of files stored on the community's local device. So it's kind of like a yellow page, which is a catalog that tells you who is where, but it's a distributed yellow page. Also, it is not a system to store files. So we only store the metadata, but the actual data remains peer-to-peer. Second, it is important to note that this system, while decentralized, still has a certain level of centrality that needs to be designed because we design evidence-driven mechanics inside the system to inform decision. And finally, most importantly, that proof of architectural work is not a proof of stake. It is by no means designed to be a financial speculation tool because work is defined to be a piece of information in the form of design content and compute. Therefore, this decentralized system has the goal to enhance built environment quality, but not profit maximization. So the blockchain is not here to enhance your capital, but the blockchain is used for social capital. And the ultimate goal is to create this computational market that circulate value for content creators in architecture. And so everyone's contribution can be acknowledged. And this comes to our last part, which is how can we abstract a generalized model for a negentropic design? And so I think this requires a shift in mindset from designing objects to designing complex systems. And it also shifts traditional architectural industry from a centralized system to a decentralized system. And it's designed around these 5 pillars. The first, how we process information should be conscious. And the process begins not with a BIM model, but the design of the data environment. And this environment should facilitate information process that enhance the pricing system by enabling participation. And this also becomes the central entropic core through collective value discovery. Second, we have to define the markup blanket, which is to design the multi-layer boundaries of the system through a stack of physical, information, and social layers. So physical will be the amount of surprises of the building design. The information would be the statistical distribution of how likely the value of the design is. And the social blanket is a prediction of how this design will perform in the real world through protocols and simulations. Third, we must embed both diversifier and validator in the system, that we should integrate AI tools consciously through generative and simulative analysis. The system must be able to run what-if scenarios to create choices. Fourth, we must enable preemptive loops. So we have to design the pathway for actions in a system, from prediction, inquiry, ranking, trigger, consensus, to actually building the design as a response to urban problem, so that we can perform through protocol as collective. And finally, we must enable micro-value feedback. So if we want to decentralize the way we produce architecture, we must decentralize the way that value can be transacted to the actual content creator, not through centralized actors. And we must do so by enabling the compression and sharing of knowledge models, such as micro IP libraries. So I can just upload a door or a window and be able to get value back for my contribution. And this will actually help a BIM environment to actually become a common data environment where everyone can contribute and benefit from it. And so net entropy is best achieved collaboratively. And this framework that I propose here is not a form of future automated architecture devoid of human touch. Instead, it tries to propose a future where architects are the designers of system intelligence, and we take the lead in decentralizing participatory urban production. So our role will become more curatorial, more strategic. We can help set the goal, design the rules of engagement, and craft the sensory and experiential quality of the space, while we leverage computational power to handle the complex real-time negotiation with entropy. It's also to prevent that generative AI take over the power of actually designing more human-centric environments. So just to conclude, our journey started from abstract theory of Shannon and Weiner to very practical application of negentropic design through a new paradigm in the generative approach. Information is the medium through which we negotiate entropy. And by understanding its dual nature, both as a source of surprise, which is the Shannon entropy, and a tool for prediction, which is the Weiner negentropy, we can transform our practice and rethink how we produce value in architectural production. Technically, it tries to propose how we can merge blockchain, BIM, and AI into a decentralized stack, but socially, it tries to enable transparent participatory planning and prevent bad voting. Economically, it tries to create a micro market for data and compute, not just financial capital. So this is more than a system design, but it's actually a governance design. It tries to enable new forms of value circularity. And so in conclusion, negentropic architecture is not just about creating perfectly controlled, sterile environment. It's actually try to use our design intelligence to create systems that can help us navigate uncertain future, preempt crisis, and facilitate participatory equity. On this note, I wanted to say that in the increasing algorithmic age, a design is not just a technical endeavor. It should be a form of social and economic engineering. And this approach is deeply ethical because the choices in a system that Shannon and Weiner indirectly spoke of is actually a form of freedom enabled by better information and better prediction. And this freedom should be distributed as widely as possible so we can build more human-centric environments. With that, I think we can start with discussion. If there's any questions, welcome to brainstorm it or any sort of discussion, or if you disagree with this entirely, I also welcome.